All right, howdy folks. I'm just going to do a couple more examples for today's topic, which is Introduction to Rationals. You've probably seen our recorded videos already for today. So in this time, I'm just going to do a couple examples that feel different to continue helping out with both the exit slip and the homework. So the big thing about rationals is they are made up of pieces. So just a big idea here. Every type of function has a unique characteristic. So for example, in Unit 2 with polynomials, those graphs were smooth and continuous. So we didn't even talk about domain very often because the domain of a polynomial is all real numbers for any polynomial. So it's kind of boring to say it every time because it never changes. But with rationals, the domain is frequently changing because the values that cause the function to be undefined are frequently changing too. So whenever a rational function gets graphed, there's going to be a line that it avoids. And again, like I said, that location of the line will change depending on the function, but you're going to end up getting things that look like this, where the behavior of the graph approaches that vertical line, but it never ever will cross it. And we call that vertical line the vertical asymptote. So what I'm going to talk about right now is just give a couple of more examples from the videos we've already had of finding the vertical asymptote and the domain of rational functions. So let's just do 4 examples. We'll start in with something fairly friendly. So let's say we are given the rational function f of x equals x plus 7 divided by x minus 2. So we know this is a rational function because it feels like a fancy fraction. Particularly in the denominator, there's a variable. So that's what makes it rational. So when you think of rational functions, kind of just think of them as fractions with variables. The way we find that vertical line that the function has to avoid is simply by grabbing the denominator and setting it to 0. And we talked about this a little bit in Unit 1, mostly from the perspective of finding domain. So the vertical asymptote language is a little new here. But the way we find the vertical asymptote is just, again, grabbing the denominator, setting it equal to 0, because we know division by 0 would be undefined, so we don't want that to happen, and then solving. So for this example, the vertical asymptote is x equals 2, and I frequently will just abbreviate vertical asymptote as VA. Now, once we have the vertical asymptote, we might as well state the domain, and the domain is going to be everything else. So if the vertical asymptote is x equals 2, the domain is everything but 2. So together, the vertical asymptote plus the domain make up all real numbers. So I can say all x such that x does not equal 2. That would be one way to express the domain as set builder notation. Or I can use interval notation to say negative infinity to 2, jump over 2, pick back up, and go to infinity. So that would be the corresponding domain. So sometimes in homework or textbooks, it'll say find the domain and then find the vertical asymptotes, but it's really fine to find them in either order, right? You guys learned how to find this domain right here back in Unit 1. But today I just found the vertical asymptote first and then let that inform the domain. So hopefully you feel the connection between those two things. The vertical asymptote and domain go hand in hand. They're not the same, they're not equal, but they are related to each other. What one is, the other is everything but that. So let's try another one. For this one, let's make our function feel a little bit more crazy. So how about we have f of x equals, let's give ourselves x squared minus 1 in the numerator, and how about we do x squared plus 8x plus 15 in the denominator, just to make it feel a little different, a little bit more going on. So same approach, let's find our vertical asymptotes first. That is only tied to the denominator. Again, division by 0 is the problem. 0 on top of a fraction is fine, right? 0 divided by a number is 0, but it's dividing by 0 that causes problems. So we'll set this denominator to 0. For this example, I made the denominator quadratic. I made it a quadratic that factors, so we don't have to get too crazy here. Two numbers that multiply to 15 and add to 8 would be 3 and 5. So it looks like our two vertical asymptotes will be -3 and have multiple vertical asymptotes. Actually, the degree of the denominator will tell you how many vertical asymptotes you have. So this was a degree 2 polynomial in the denominator, therefore there are 2 vertical asymptotes. In the last example, the denominator was degree 1, so there was only 1 vertical asymptote. If I made a denominator with like a cubed polynomial, right, a degree 3 polynomial on bottom, then there would be 3 vertical asymptotes. So there is that direct relationship there. Okay, so since we've got the vertical asymptotes, you guys know the domain follows. Still giving those 2 options for writing domain. I don't know what everybody's favorite is, so I just keep using both. But we can say either all x are good, such that x does not equal to, I'll put the -5 first and then the -3. It's nice to kind of put those in numerical order. So -5 is less than -3. And then my set builder folks will say -infinity to -5, unioned with -5 to -3, unioned with -3 to infinity. And that would be the domain for that one. So whatever the vertical asymptotes are, the domain is everything but that. So hopefully this is feeling pretty comfortable. Let's try another. I'm just trying to throw all the curveballs I could possibly think of at you guys. If I gave you f of x equals, how about x plus 11 divided by x? This is another one that I know in the past has maybe tripped people up a little bit, almost because it's too simple. So basically what we're going to do here is same as before, snag the denominator, set it to 0, and solve. And all that's happening here is when you set the denominator to 0, the solving is done, and the vertical asymptote is just x equals 0. So that one didn't take too much work. From there, the domain is thus everything but 0. So all x such that x does not equal 0, or -infinity to 0, unioned with 0 to infinity. So what's your preference, set builder or interval? Feel free to let me know. Normally there's kind of a split, so that's why I keep using both. But it's good to be comfortable with both. The last example I'll do is another that I've just kind of in the past seen as one that can cause some confusion. It's kind of a rational look-alike, and that would be something like, how about x minus 17 divided by 5? So let's just take the same approach we have in the last 3 examples, snag the denominator, set it to 0, and solve. So the denominator is 5, we set it to 0 and solve. What feels different, I hope, about this one is there's actually not a variable in the denominator. So we've actually just created a statement which is false and can never be true. In other words, there's no value that makes the denominator 0 because there's no variable down there. So this implies there's actually no vertical asymptotes. So this function is technically not even rational, although it may appear to be, which I'll talk more about in just a second. The fact that there are no vertical asymptotes tells me there are no values to throw out from the domain. So the domain is everything. And to say all real numbers, I could just say, okay, all x, such that x is a real number. That would be one way, using set builder notation to say there are no restrictions, everything's fine. My interval folks, you get to say -infinity to infinity. So the reason I wanted to talk just a little bit more about this one is sometimes functions appear to be a certain category, but upon further investigation, you notice they're actually something else. And I would say that's what's happening with this function. So if I rewrite f of x equals x minus 17 over 5, we know with our knowledge of fractions that that's the same as saying x over 5 minus 17 over 5. So I can break it up to 2 separate fractions. And to go even a step further, I'm going to say that x over 5, or 1x over 5, is actually the same as just 1/5 x. minus 17/5. When I take those few steps of rewriting the function, what type of function would you now say this is? Is it truly rational, or is it something we know more from the past? And hopefully you're saying, actually, yeah, it's a polynomial, right? So polynomials, all polynomials have domains of all real numbers. And even more specifically, it's a linear function. So you may remember from the past this y equals mx plus b feel, and I would say that's exactly what this function has. So this last example is, in fact, a linear function disguising itself to make it feel like a rational, but it's actually not. So I think that's kind of all the tips and tricks I can give you guys related to the domain and the vertical asymptote. This should be adequate to for sure do today's exit slip, as well as the first 4 problems in the homework. So give me some feedback. Let me know how you're doing. Let me know if this helped, and I'm happy to do something like this again. Alrighty, take care.